Hello, my name is Kevin Kelly. I'm a postdoc in the theory group at Fermilab, and I'm going to tell you about some recent work concerning leptonic unitarity, our current understanding, and some future prospects. This is based on a paper from last year with my collaborators Sebastian Ellis and Shirley Lee. So just a brief outline of what I'm going to tell you about today. First, I'm going to assume that we know that unitarity is a tenet of our theory with leptonic mixing, and I'm going to address what we currently know about leptonic mixing. Can we over-constrain this system given our current experimental data, and how large is CP violation in the lepton sector? If we don't assume unitarity, however, things are a little more challenging. I'll talk about different probes of whether or not the mixing matrix is unitary, what experimental data can say now, and what future experimental data will have to say about this. So first, let me give a very brief overview of what 3-neutrino mixing with unitarity looks like. We adopt this canonical parameterization known as the PMNS matrix. This describes the mixing between the neutrino mass eigenstates and the flavor eigenstates. It requires 3 mixing angles, theta 1, 2, theta 1, 3, and theta 2, 3, and 1 CP violating phase, delta CP, to describe this unitary 3x3 mixing matrix. The other ingredient that's important for neutrino oscillations is that the mass eigenstates have distinct masses. Neutrino oscillations are sensitive to the mass squared splittings. So for instance, m2 squared minus m1 squared. And that we know that there are 2 distinct non-zero mass squared splittings. It's unclear whether the pattern of these eigenstates is in the so-called normal ordering, where M1 is less than M2 is less than M3, or in this inverted ordering where M3 is the lightest, then M1, then M2. So in our paper from last year, my colleagues and I assumed that we know some things about oscillations perfectly. For instance, if you measure a muon neutrino converting to an electron neutrino at long baselines perfectly, and you measure the amplitude, what can you learn about these mixing angles? And the result that we saw is what's shown here. In the left panel, we're showing how different experiments can give us information on the reactor mixing angle, theta 1, 3, versus the solar mixing angle, theta 1, 2. And in the right panel, we're showing that reactor mixing angle again against this atmospheric mixing angle, theta 2, 3. For instance, if you measure short baseline reactor anti-neutrino oscillations, nu bar surviving as nu bar, then you're highly sensitive to this mixing angle theta 1, 3. So if you make a perfect measurement of those oscillations, you would end up with a measurement in these planes that corresponds to these straight blue lines. However, different oscillation channels at different baselines and with different energies would give you measurements of different combinations of angles. For instance, if you measure nu mu oscillating into nu e at long baselines, for instance, what's currently being done by the NOVA and T2K experiments, and if you measured that amplitude perfectly, you would end up with a measurement in these planes given by this orange line. As you can see, all of these different probes, if measured perfectly, would agree at a point in this right panel. It would agree at this point here, and in the left panel down here. Those points correspond to our best current knowledge of these 3 mixing angles. Now, of course, this is an ideal, perfect construction of these types of measurements. We can ask, what do current experiments actually have to say about this? And the results are shown here. This is, again, what we think the current experiments know today about these mixing angles and their respective uncertainties on these measurements. The general regions encompassed by each of these experimental probes matches those perfect amplitude measurements I showed on the previous slide, but now with some spread in the measurements. However, these measurements all agree at this overlap point in the right panel for a relatively large atmospheric mixing angle and a relatively small reactor mixing angle, and then in this left panel for the same value of the reactor mixing angle and a relatively large solar mixing angle. So the fact that all of these very different probes, for instance, solar neutrino measurements or long baseline atmospheric or atmospheric neutrino measurements all agree is a good indication that this picture of 3-neutrino mixing is a pretty solid one. However, it's all going under this assumption that we can parameterize this mixing matrix in terms of 3 angles in one phase. So we wanted to ask the question, what happens if we abandon the assumption that this is a 3x3 unitary matrix? Well, in order to do so, we have to abandon this PM&S parameterization and adopt a new one. So the one that we did is what's shown here, labeled as ULMM for leptonic mixing matrix. We parameterize this matrix in terms of 9 magnitudes of the 9 different elements of the mixing matrix, as well as 4 complex phases that we label with the UE2 element, the U tau 2, the UE3, and the U tau 3 element. This is a total of 13 free parameters instead of 4. So in a sense, it can be thought of as the 4 original parameters plus 9 conditions that have to be met in order for the mixing matrix to be unitary. What are those conditions? Well, we can construct an overcomplete set of these conditions that have to do with the object UU dagger or U dagger U. If you dot U into its complex transpose or vice versa, then you must, if U is unitary, you must end up with an identity matrix. So other ways to write this are in terms of amplitude squared of elements and elements times complex conjugates of elements, corresponding to what we consider to be normalizations that we call N alpha and NK, and triangle closures, which we label as T alpha beta and TKL. N alpha equals 1 is the condition that each of the 3 rows, when we construct U dagger, have to normalize to 1. And likewise, NK correspond to the 3 columns being normalized to 1. T alpha beta and TKL correspond to closures when we effectively dot one row or column of the matrix into another. And these must be 0 in order for the mixing matrix to be unitary. So about 6 years ago, Stephen Park and Mark Ross-Lonergan performed an excellent study of leptonic unitarity, given what we knew around 2015. So the results I'm going to show are consistent with those from this previous paper, except with some more up-to-date data, especially T2K and NOVA. What they found is that the normalization conditions are met at roughly the 1% level for the muon and electron rows, and then the columns and the tau row normalization are constrained at roughly the 10% level. They also analyzed the magnitude to which these triangles are closed and found that the E mu row triangle is the one that's the most constrained. Now, if you are familiar with stereo neutrino searches, especially at short baselines, these are highly sensitive to the non-closure between different rows of the unitarity of the leptonic mixing matrix. Column triangle closures are more difficult to constrain, and these constraints come from an indirect source of what we call Cauchy-Schwarz inequalities. Where this comes from is a theoretical argument. If the leptonic mixing matrix isn't unitary, it's reasonable to ask what the source of this non-unitarity is. A straightforward explanation that many adopt is that there are new particles involved in neutrino oscillations, for instance, heavy sterile neutrinos, that in principle take a 3x3 mixing matrix to be a larger one, 3 plus n, where n is the number of sterile neutrinos. And the 3x3 leptonic mixing matrix that we observe in oscillations is just a subset of a larger unitary matrix. And then small deviations from unitarity will appear in that 3x3 submatrix because of this extended matrix. So if this is the case, if U is a submatrix of a larger unitary one, we can write down some further restrictions. Specifically, the closure between different rows of the 3x3 mixing matrix is constrained by these normalization conditions. So for instance, the magnitude of the closure of a triangle between row alpha and row beta, the magnitude squared of that has to be less than or equal to the deviation from normalization of the alpha row and the beta row. However, this is a theoretical assumption, and so we wanted to ask whether it's well motivated and whether we obtain qualitatively different results if we assume this submatrix case versus not. So first, if we're agnostic to why we don't have unitarity, we asked how well do we know the elements of the mixing matrix? This shows our knowledge today in blue, as well as some projections towards the next decade or so of experimental data in red. Each of the elements is shown as a single panel. I'll note that the UE3 panel in the top right has the value multiplied by 10 just to make it on a similar scale with the other elements here. What you can see here is that most of these elements are pretty well known, with the exception of the tau row, which are relatively unconstrained. But with about another decade of experimental data, these will all improve drastically, with the exception of that UE3, which is very well constrained already. We can also ask how well the normalization conditions are known given current data. This is what we find for the row normalizations. Again, all three of these, NE, N mu, and N tau, should be equal to 1 if the mixing matrix is unitary. We find that the current data are all consistent with that assumption, and that future data will be able to improve by about a factor of 2 or so in these different measurements in about a decade. For measuring the electron row normalization, that improvement will come mostly from the Juno reactor neutrino experiment in China, whereas this much bigger than factor of 2 improvement in the tau row normalization will come from the IceCube upgrade and IceCube Gen 2, as well as some assistance from Dune's measurements of tau neutrino appearance in a long baseline beam. In terms of the column normalizations, we're showing these measurements again at 95 and 99% credibility. Each measurement will improve considerably going forward, and this is mostly driven by the improvement of measuring these tau row elements at IceCube and Dune. We can also ask how well we can constrain these triangle closures. Now, there are 6 different triangles relating to pairwise contractions of 3 different rows and 3 different columns. And instead of plotting the constraints on the magnitude of those closures, we chose instead to look at the real and imaginary part of those triangle closures. What we see is that the constraints that we get are similar to that Park and Ross-Lonergan paper, where the constraints on the row closure normalizations are given by stereoneutrino searches, but will have improvement in the next decade from long baseline experiments. Then the column normalizations are more difficult to constrain, and the constraints tend to be weaker in those panels. But now let me revisit this assumption that we made about the source of the lack of unitarity in the leptonic mixing matrix. I said that we wanted to be agnostic just to see whether the assumption is a well-motivated one or not. But now we're going to revisit this assumption and look at these Cauchy-Schwarz inequalities that give some indirect constraints on the triangle closures from the normalization conditions. Now we can revisit this submatrix assumption on the measurements of the magnitudes of the different mixing matrix elements. This is now comparing current data under 2 different assumptions. The blue lines correspond to our agnostic assumption, where we did not give any prior on the source of the lack of unitarity in the matrix, whereas now the green lines assume that U is a submatrix of a larger unitary one. For instance, if there are heavy stereoneutrinos leading to this non-unitarity. What you can see in comparing these 2 assumptions is that the electron row in the top and the muon row in the middle tend to largely agree, with some small deviations. However, this submatrix assumption leads to significantly more constrained measurements of the tau elements, as well as preferring smaller values across the board of those tau elements. We can also look at how this assumption changes our analysis in terms of measuring the closures of different triangles. So again, this is all comparing current oscillation data under the agnostic assumption in blue and the submatrix assumption that U is a submatrix of a larger unitary matrix in green. The top correspond to these row closures, and again, the constraints under these 2 different assumptions are largely the same. The submatrix assumption leads to slightly tighter measurements of the TE mu triangle and the TE tau one, whereas the T mu tau triangle returns about exactly the same measurements, with the green and the blue nearly overlapping in these planes. And then in the column closures, T12, T13, and T23, the submatrix assumption leads to pretty significantly smaller allowed regions in these planes. And this comes from the fact that we have relatively strong normalization measurements of the different columns that provide additional handles on these different triangles in the bottom row that aren't present in the agnostic case. So let me conclude by just saying that looking at all of the oscillation data that we have to date and what is coming in the next generation, by dividing these up into different measurements, for instance, looking at their measurements in terms of different mixing angles, can actually serve as an important check to see whether the three neutrino hypothesis is a good one or not. The current data can also serve as a constraint on whether or not the leptonic mixing matrix is unitary or not at the few percent level. And next generation data, specifically from Juno, IceCube, Dune, and Hyperkamiokanda, will improve all of these constraints by about a factor of 2 in the next decade or so. If we make different assumptions about the origin of non-unitarity, we can lead to even stronger constraints, but allowing for these different types of analyses, these agnostic or submatrix ones, can see whether one or the other is a better proxy for how these neutrinos are oscillating, and it eventually, hopefully, lead to some new discoveries in the neutrino sector. So thank you very much for your attention, and I hope to answer as many questions as possible in the Q&A session. I look forward to interacting with everyone throughout the conference. Bye.